p99 latency jumped from 200 ms to 4 seconds within 10 minutes of peak traffic. The product page code fetched the product object, then looped through each review ID and executed a separate select query, 101 database round trips for 100 reviews. Under peak load, the database connection pool saturated, queries queued, and latency exploded. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover application performance monitoring. APM sits between infrastructure monitoring and user experience monitoring. It instruments your code to track request paths, database queries, and error rates. Without it, you're flying blind on issues like N+1 queries that silently degrade performance. APM rests on 3 types of telemetry. Metrics tell you something is wrong, traces tell you where, and logs tell you why. You need all 3 to debug effectively. Here's a production-grade OpenTelemetry instrumentation class for a Java service. It configures an OTLP exporter, sets service resource attributes, and provides methods to instrument database queries and external API calls with custom spans. The red method, rate, errors, duration, is the standard for service-level monitoring. For every service, track these 3 metrics, and you'll know instantly whether users are happy. This code implements red metrics using Prometheus Client Library. It defines counters for requests and errors, and a histogram for duration with carefully chosen buckets to capture P50, P95, and P99 latency. In microservices, a single request passes through many services. Distributed tracing creates a tree of spans, each representing a unit of work, and propagates a trace ID across service boundaries so you can see the full journey. This code demonstrates distributed tracing with context propagation. The callOrderService method starts a child span and makes an HTTP call. The handleIncomingRequest method extracts trace context from incoming headers to continue the trace. APM is the feedback mechanism that tells you whether your last deployment improved anything. It answers the 3 questions that matter. What's slow? Where is the slowness happening? Why is it happening now? Here's a minimal APM configuration for a payment service. It tracks p99 latency, error rate, and update score with alerts that fire on user-facing thresholds, not CPU. Modern APM has 4 layers. End-user experience monitoring captures how humans experience your app. Runtime instrumentation measures what your code actually does. Infrastructure monitoring correlates with app data. Transaction tracing maps every service call. This configuration shows a complete APM stack for microservices. It includes RUM for end-user monitoring, runtime instrumentation for multiple languages, infrastructure metrics, and probabilistic tracing at 10% sampling. These 4 metrics cover 80% of production incidents. Latency percentiles reveal outliers, error rate as a percentage catches SLO breaches, saturation warns before collapse, and throughput provides context. This config shows the 4 essential metrics for an API gateway with alarm thresholds. Note that p99 latency is measured per endpoint, not per node, to avoid hiding slow endpoints. In Kubernetes, you need pod-level granularity. Use eBPF-based auto-instrumentation to capture traffic without code changes, and tag traces with Kubernetes metadata so you can correlate a rollout with an anomaly. This pod configuration injects Kubernetes metadata into OpenTelemetry resource attributes. Now every trace includes the pod name and node name, enabling drill down to the exact container that caused a latency spike. Real-time alerting means acting on fresh data with context. Use sliding windows and dynamic baselines. When a page fires, it must include a trace ID and a runbook link, or it's just noise. This Prometheus alert rule fires when the error rate exceeds 2% for 3 minutes. It includes a runbook link and trace ID in the notification, so the on-call engineer has immediate context. Traces show you where a problem occurred, but logs hold the details: stack traces, user IDs, exact SQL. Centralize logs with a structured schema and include the trace ID to connect log lines to APM spans. Enforce a logging schema like this across all services. The traced field is the bridge between logs and APM spans. Always emit structured JSON, never parse logs in your aggregation pipeline. This is the same issue we highlighted at the start. Here's exactly why that happened. The product page code fetched the product object, then looped through each review ID and executed a separate select query. With 100 reviews per product, that's 101 database round trips. Under peak load, the connection pool saturated, queries queued, and latency exploded. The fix was to change the code to use a single join query. Select from products left join reviews on products it equals reviews producted where products it equals. They also added eager loading, an index on reviews producted, and an APM custom span to measure query time. After the fix, page latency dropped to 150 ms even at peak traffic, and database CPU dropped to 25%. This is the exact pattern that caused the Black Friday incident. Each iteration of the loop executes a separate database query. With 100 reviews, that's 101 queries. Always use joins or eager loading to fetch related data in a single query. Average latency hides outliers. A service could have 1,000 requests at 1 ms and 1 at 1,000 ms, average 2 ms, but 0.1% of users had a terrible experience. Always track p99 latency for user-facing SLOs. Without trace context propagation, each service starts a new trace, and you lose the end-to-end view. Always use OpenTelemetry auto-instrumentation or manually inject the traceparent header to maintain the trace across service boundaries. The Java code examples use OpenTelemetry SDK 1x APIs. If you are using an older version, 0x, the setAttribute method was named putAttribute, and the resource builder API differs. Always check the current OpenTelemetry Java SDK migration guide when upgrading. The article mentions tail-based sampling for slow requests, but doesn't show configuration. Here is a minimal OpenTelemetry collector config that samples 100% of traces with duration 500 ms and 100% of errors, while dropping fast, successful traces. The article explains that N+1 queries cause latency spikes without CPU increase because the app server is idle waiting for database responses. This is a classic I/O-bound pattern. The bottleneck is network round trips and database connection saturation, not computation. Always monitor database connection pool usage and query count per request, not just CPU. The article shows a generic database query span. Here is a concrete example using JDBC with automatic instrumentation via OpenTelemetry JDBC wrapper, which captures SQL statements and execution time without manual span creation. When you suspect an N+1 query, start by checking APM traces for the number of database spans per request. Then use pgstat statements to find the top queries by total time. Look for patterns like many identical select queries in a single trace. Let's run through some common interview questions. What is the red method? Rate, errors, duration for service level monitoring. How do you detect an N+1 query in production? Look for many identical select statements in a single trace. Why might CPU be low while latency is high? The app is waiting on I/O database network, not CPU bound. And a few frequently asked questions. What is the difference between metrics and traces? Metrics are aggregated numbers. Traces are individual request journeys. How much overhead does OpenTelemetry add? 5% CPU when sampling at 1%. Should I alert on CPU usage? No, alert on user-facing metrics like p99 latency and error rate first. To recap, APM provides the visibility you need to catch N+1 queries and other hidden bottlenecks. Start with red metrics, instrument every external call as a span, and always propagate trace context. Alert on p99 latency and error rate, not CPU. Ready to go deeper? Up next, distributed tracing with Jaeger, then SLI, SLO, SLA explained, then alerting and on-call best practices. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.